Our first speaker is Professor Frazer Pearce. Are you here, Fraser? That's Fraser, right. Fraser was born in Nottingham, and he's now a professor at the University of Nottingham in the physics department. He was previously at Durham and Sussex universities, and he specialises in astrophysical simulations using some of the world's largest supercomputers. He's interested in structure formation of galaxies and galaxy clusters. And he co-leads a project called the 300 Project, which is a collaboration of over 30 institutions. And his talk is going to be about adventures in the Goldilocks Zone, the search for other Earths. Professor Frazer Pearce.
We'll lower the lights when I get started. Can everyone hear me? You'll notice I got rid of the feedback. I don't know why they do that. And apologies for the heat in here as well. We don't have any actual control over the air conditioning because we're not allowed. So we've tried to keep the doors open to keep the heat down a bit. Welcome to Nottingham. You'll have also noticed that the university has laid on an open day for you while you're here. So, if anybody would like to chat to the department about physics in Nottingham, you're more than welcome to go and chat to the helpers downstairs at some point during the day. They'll tell you all about what goes on here as an undergraduate. Today, I'm going to talk about the search for other Earths. And a little bit about planet formation as we know it. So I'm going to start here, though, which is something that many of you will be familiar with, which is the solar system. So across the top is, it's to scale in terms of size of the planets, but it's not to scale in terms of their position. Okay. So this is the solar system. 4 rocky planets, 4 gas giants. You'll have noticed straight away that this doesn't look random. I mean, it would be sort of surprising if all the rocky planets turned out to be on the inside and all the gas giants turned out to be on the outside, if that wasn't due to some form of physics. Anyone know what the physics is? Why are all the gas giants on the outside and the rocky planets on the inside? Yeah, exactly. It's hot, right? There's a big thing here in the middle, the sun, and that's hot. And so as you move away from the hot thing, it gets cooler. As we go out here, it gets colder and colder. And at some point, volatiles can condense, and that's called the snow line. And beyond that, you get lots and lots of volatiles, and that's why the big things are on the outside and the rocky things are on the inside, fundamentally. Okay, so that's the solar system. Along the bottom is the solar system again, but this time with the correct scaling in terms of distance from the sun in the middle. So all of the rocky planets are here in the middle, but they're all compressed into this little bit. The Earth is at 1 astronomical unit. Okay, so that's in here, and then we have the 4 gas giants further out. So Jupiter's sort of at 5.2. Jupiter's at 5, then Saturn at 10, Uranus at 20, Neptune at 30. Okay. And you can straight away see that this spacing looks a little bit surprising, right? It goes 5, 10, 20, 30 in terms of multiples of the distance of the Earth from the Sun. And that should strike you as a little bit odd. We'll come back to that later. Okay. Does anyone object if I do some mathematics? Yeah. I'm promising to do it. I'll make you do a little bit of it. Right, okay. I wasn't sure whether I was going to bother, but I'm going to turn the lights up a bit. So you can see. So here's the sun. Okay? Here's a planet. The sun has mass m, the planet has mass little m. This distance is r, the distance of the planet from the sun. The planet goes round a big circle, roughly a circle, like that. Oops. You can see that my artist days are long behind me, right? Okay? The period, right, equals the distance all the way around divided by how fast it's moving. Okay? So that's 2 pi r, the distance all the way around that circle, divided by velocity. Okay? So I can rearrange that like that. Okay? So I've just squared it, swapped the p and the v over. Okay? Now, what's making that planet go round in a circle? Why? Everything moves in a... Gravity, yeah, exactly. Because everything moves in a state of rest or uniform motion unless it's acted on by an external force. Right, so there must be a force. Force is gravity. Okay? So, Gmm over r squared, Newton's law of gravitation, equals the force. Right? And that's equal to the mass times the acceleration. F equals ma. Right? And the acceleration is making it go around in the circle, so that's just centripetal force. So that's mv squared over r. Okay, v squared over r is the acceleration because it's going around in a circle. And we've got v squared. See, there was a reason why I did that first. Right? So that is m 4 pi squared r squared over p squared r from there. Okay? Now we can cancel some things. Well, that m and that m cancel. Right? Take the p squared over there. P squared equals 4 pi squared over gm. Lots of r's cancel. R squared on the bottom. R cubed. Which is? Kepler's law, yeah. Isn't that great? Kepler's law in 2 lines. Right? So, what does that? Why did we bother? So there's a relationship between the period and the radius. Okay? And the period squared goes like the radius cubed. And there's a constant of proportionality, which depends on the mass of the thing you're orbiting, the star. Okay? So this constant of proportionality will change depending on how big the star is. Okay? But fundamentally, everything in the universe obeys this law if it's going around in an orbit. So things that you're observing, right? Those things that you're looking at, right? If you can measure the period of something, you know how far apart they are. Which is neat, right? So we'll come back to that later. Right, back down to dim lights. That's the end of the mathematics. Right. So, I promised to talk a little bit about planets formation. This is a T Tauri star. It is actually T Tauri. So when stars form, it's a messy process. Okay? The idea that a cloud of gas collapses and forms a star and everything around it's pristine and it all falls into the star and forms a star is obviously not what happens. When the star forms, there's a star forming in the middle of this little thing in the middle. Lots and lots of stuff gets left behind. Right? This is an observation, not a model. Right? It's actually it's from CFHT. It's actually a picture of T Tauri, a star forming in the middle. Lots of stuff left behind. Okay. A little bit later than that, if you look, say, using this is a whole set of images taken with the Atacama telescope. This is a radio telescope. These are again observations, not models. What you see is the star in the middle, but surrounding them there are these debris disks. Stuff gets left behind, junk, stuff that things can form out of. But you can see in these things that actually not only is these don't look smooth. They're not just smooth disks. You can see these lanes carved out, right? In multiple ones of them. Okay? And what's carving out those lanes? Planets. Yeah. Things in resonance. Things that are orbiting. It's a bit like it should be reminiscent of Saturn's rings, for instance. Right? But on a much, much bigger scale. Okay? So this is observations. This is not something that someone's dreamed up as a theorist. I'm a theorist, by the way. It's not something that someone like me would have thought up. Right? These are actual, take a telescope, take a radio telescope in this case, and make observations. And this is what you get. It's one of the most amazing images that's come out in the last few years, in fact, set of images. And if you actually do a model, here are a couple of different groups, made some models of what happens when a star forms, and you get a debris disk around it, and you start to allow the debris to accumulate, form planets. You see exactly the same thing, right? You see planets forming, and you see these big regions carved out within the disk. You see these spiral patterns within the disk. Again, it's very reminiscent of the sort of thing that you see in Saturn's rings, essentially. The planets are carving out gaps in the disk. Okay? And what's going on, what's driving a lot of this is a thing called resonance. Okay? And so resonance is something we see a lot, and we talk a lot about it in physics. And here's an example, for instance, of something where resonance came along and surprised people, right? So resonance is when you have a driving force, but it happens with a regular period, okay? And what happens is, in this case, everyone stepped, and then as the bridge started to move, you step in sequence, right? Don't march across this bridge. Remember those signs, right? You step in sequence, and that caused the whole structure. That causes the whole structure. Play that again. That causes the whole structure to rock backwards and forwards. Oops, why has that not worked? I don't know why that doesn't want to play again. Oh well. That causes the whole structure to move in sync with the people stepping across the bridge. And it very much surprised the engineers who built the bridge, the designers who built the bridge, not the engineers, the designers who built the bridge, very much surprised them how much of an oscillation it drove in that Millennium Bridge across the Thames. But resonance happens all over physics. We're going to hear about it again multiple times in this talk, which is why I brought it up as a thing. But it's a real world phenomenon. We see it a lot in many physical things. You hear it when you play music, and you see it in the real world. But it also has an impact on the solar system, which is what we started with. So this is sort of the current view of the solar system and how the early solar system and how it formed. So the top row is pretty much what was happening within the debris disk early on, so year zero at the beginning. Okay, so in that case, you get Jupiter, this big red ball. Forms at the snow line, okay? It's where lots of volatiles can condense, forms a big gas giant, okay? And now inside there, it's all rocky because it's inside the snow line and volatiles can't condense onto the objects. And outside there, you get sort of cometary material, lots of debris, but it's water rich because there you can get condensation. So you have this split. Inside the snow line, it's dry, and outside the snow line, it's wet, okay? But then you get some planetary migration, like we saw in those earlier, where those things were carved out. So what happens is that a force acts, and there's slightly more force causing the planet to move in than move out in these setups. And so Jupiter migrates inwards, and it's a big planet, so it makes a big mess. It stirs up the solar system So as it migrates inwards, you end up with it throwing around all of these water-rich things and all of the water-poor things and mixing them up. Okay, so Jupiter moves inwards. And it would indeed just crash into the Sun if you just let that go on forever. But what happens is something a bit strange. Saturn also forms, sort of the next in line, and it also migrates inwards. But Saturn is less massive than Jupiter, so it turns out it migrates a little bit faster. So it catches Jupiter up in this migration. Okay? But as it catches it up, it falls into, or it crosses at the 3:2 resonance, because period is related to radius, right? And so as it moves in, its period changes. Right? And so eventually it reaches a point where it's going around twice for every 3 times the planet inside it, Jupiter's going around. Okay, and that's called a resonance, because you've got 3 orbits and 2 orbits. They're locked together. And then what happens is that Jupiter and Saturn as a system get stuck in that 3:2 resonance. And it turns out that 2 planets in resonance don't migrate in anymore, they migrate out. So you have both planets migrating in until they hit the resonance, and then they start migrating back out again. And that's called the Great Tack. A bit after yachting, right? So now you get outward migration. So Jupiter and Saturn now move back out again. You may think, this sounds awfully complicated, right? But it explains a lot of things about how the solar system looks like it does today. And one of the things it explains is, well, two of the things it explains. One of the things it explains is why is there so much water in the inner solar system now? Why do we have water? So much water. What's the average depth of the ocean?
4,000 meters?
Yeah, a lot, right? 4 kilometers. Right, so if you just jump out of a plane somewhere on the Earth, you land in the sea, you've got 4,000 meters of water underneath you, on average. That's incredibly deep, right? It's quite surprising. Right? There's a lot of water on the planet Earth, but there shouldn't be, right? Because we're inside the snow line. So that water has to have come from somewhere. So this is one of the ways that you can explain why there's so much water in the inner solar system, because actually all this wandering about mixed everything up, stirred everything around. Right? And the other thing it explains, or helps to explain, is why Mars is so light. Right? You would expect in those disks, right, the closer you are in the middle, into the middle, the less material you have to grab. The further out you are, you've got more thing in your orbit, because the orbit grows as r. Right? So you should have more material, so you should become more massive. But Mars is only 10% of the mass of the Earth, 11% of the mass of the Earth. Right? So that's sort of surprising. But all this wandering around, all this gets cleaned out, you see. Jupiter gobbles it all up. And so there's not much material in here for Mars to grab. Okay, so this great tack explains water, and it also explains the funny mass ratios of the planets. Okay? But the one question is why are Jupiter and Saturn no longer in a 3:2 resonance? Because this all is predicated on Jupiter and Saturn being in a resonance. They're not in a resonance now, not quite, but they're close. And this sort of it helps explain the funny spacing that we saw in the early thing, right? It's the residue of a resonance, but it's not perfect. And the reason it's not perfect, the reason we think it's not perfect, is because what we think happened is that there was actually not 4 gas giants in the early solar system, but 5. So there were Jupiter, Saturn, Neptune and Uranus, plus another one. And then that 5th one had a close encounter, probably with one of these pair, and that broke the resonance between Jupiter and Saturn, and it got flung out of the solar system. So we think that early on, that's called the niche scenario, we think that early on in the solar system there was a 5th gas giant, which will be somewhere but thrown out of the solar system, quite possibly. And that's how we end up with the solar system that looks like the one we've got now. Right? So it's the residue of the resonance. But there's a lot of motion going on in that early solar system. It's not just everything formed in situ and it stayed like that forever. Okay. Everyone happy with that?
Just a quick
Yeah.
question. You've got timescale on there from year 0 to year 600.
Yeah.
Is that really? It happens all in...
It's surprisingly fast. I'm not sure how certain they are about that timescale in terms of how quickly it moves around. That will have come from the model of how that migration works. I would think it's quite relatively flexible. Because it's so short.
Yeah, I mean,
Right.
600,000 is nothing.
Yeah, so it's less than 1 million years. Yeah, it's
Is that Earth years or Jupiter years?
Earth years. That's in Earth years. We do know the time of the formation of the solar system incredibly accurately, 4.567 billion years, right? It's incredibly accurate. So it is surprising. I mean, we can date a lot of these things amazingly accurately. That's a whole different talk as how to do that to that level of accuracy. You should be amazed, right? We can tell when the solar system formed to within like 1 million years from like 4.5 billion years in the future, right? That should be stunningly amazing. So we do have this amazing handle, but so astronomers, I would have put this down. Astronomers do this for when they're uncertain, and they do this when they're really uncertain. Right? And I would say we're in this sort of mode, right? But I'm a theorist, right? Yeah, I would wave my arms a lot over those numbers. So I'm going to move on to something slightly different, just to keep adding things that are interesting. Extrasolar planetary detection. Here's one of the main ways. This is how Kepler. This is one of the main ways of doing it. There are lots of other ways of doing it, and again, that's a totally different talk as to how we do it in multiple different ways. But here's how the one we're going to talk about today works. So what happens is you stare at another star, and you just measure its luminosity up the side here. In fact, what's plotted here is the change in luminosity. So you measure its luminosity, and it wobbles up and down a bit because of atmospheric. It's coming through the atmosphere, and it'll twinkle and all that sort of stuff. It goes up and down a little bit. But what happens is a planet goes across the surface. So it happens to be aligned, that solar system, so it's got an inclination of essentially 0 degrees. So it's going across your line of sight. The planet goes across, and you see this big dip, or a dip, 2% of the luminosity. And you see a dip, and you can then say, oh, that looks like a planet going across. Right? Of course, there are other things it could be. It could be a sunspot. Same sort of effect. Of course, the planet will go round periodically. You see it again, and the planet won't change its period, whereas sunspots will over time. Right? So you can just keep watching, right? And you wait for it to come back. You can measure the period. If you know the period, you know how far away from the star it is, what the radius of that orbit is. So that's all quite neat. Just to give you an idea about whether you can do this, this data comes from the roof of St Andrews University, from I think it's a 12-inch. So you can do it with perfect accessible scopes. You can actually go and read off from the exoplanets database a whole list of planets, stars you can look at. You can do this yourselves. So you can see an extrasolar planet. I mean, if you think that is seeing it, right? You can see it yourself. Right? Just measure the flux. See the dip, there you go. And you can read off when that's going to happen from the database. So this is how extrasolar planetary detection is done, or one of the ways of doing it, just watching a star and looking at it dip. The other thing we need to talk about is the Goldilocks Zone. So the Goldilocks Zone is just the region near a star where it's not too hot and it's not too cold. Okay? So as we talked right at the beginning, near the star it's hot. As you move away, it gets cooler and cooler and cooler as you go out. Okay? So you can calculate for any star what distance away from the star is the ambient temperature 0, right? Ice. And at what temperature, well, actually first, it's 100 degrees, because it's getting cooler. So one radius, it'll be boiling water. You go a bit further out, it'll be ice. And that distance between where it's boiling and where it's ice is called the Goldilocks Zone. Okay? Now, the thing to bear in mind is that won't be the same distance from the star for every star. Right? Because the bigger the star is, the hotter it is. Right? Big stars burn bright. Right? So if you have a small star, it'll be a red dwarf, something smaller, or even a brown dwarf. It'll be less hot, smaller, burning less brightly. So the Goldilocks zone will be much closer in that case. If you take a big if you take a really big star, it'll be much, much hotter, and the Goldilocks zone will be much further out from that star. So if you know the star you're looking at, you can calculate where the Goldilocks zone is. And you can just do that because there's a relationship between the spectrum you get of the star and its surface temperature, because a star just emits in the black body spectrum, so you can just measure what its surface temperature is. And that will tell you, using the Stefan-Boltzmann law, how far away you need to be in the Goldilocks zone. So you can calculate this curve for any star. So the Goldilocks zone is calculatable. It's just the region where there's liquid water around the star. Now, there are some caveats for that, of course, because there are plenty of places, several places inside our solar system where we think there are liquid water, but they're not. It's not in the Goldilocks zone. For instance, Callisto. Right, so there are places where you could think of liquid oceans in funny places, but for the purposes of this talk, I'm talking about planetary surfaces that are possibly having liquid on the surface and therefore host to normal life. Okay. So that brings us on to this system, because it's amazing. Some of you will have come across this system before. It's called TRAPPIST-1. So this is a system where we detected 7 planets crossing the star in the same way as I showed you earlier. Right? 7 planets crossing the surface of this star. Okay? And it turns out they're all Earth masses, round about the Earth's mass. Okay? So they're Earth mass planets. They cross the line of sight of this star. So TRAPPIST is actually much smaller than our Sun. So it's just a little bit bigger than Jupiter, actually, in size, which is one of the reasons why we can detect these Earth-sized planets around it, because it's got a much smaller disk than the Sun. So when the Earth goes across, it blocks out some significant amount of light. And you might say, well, do I really believe we can detect 7 things in the same way as I showed you earlier? Well, here's the data. So you can see whether you believe it yourselves. So this is the same thing as I showed you for the St Andrews Observatory, but now for the TRAPPIST system. So these are the 7 planets, and those are the detections. So you can see that they're actually quite believable. They've been offset just to give you an idea of, just to separate them, but each of them, the dip that's associated with the planet is quite believable for all of them. And the outer one's a little bit less certain as to what its period is, but all the others are pretty solid. Okay. So there are 7 Earth-like planets in this system. Earth-sized planets, not Earth-like, I should say, in this system. The system is a bit strange because, as I said earlier, TRAPPIST is the star is much smaller than the Sun. So the Sun's there on the top for scale. It's only a little bit bigger than Jupiter, as I said. And so these 7 planets are actually pretty good. If you think of where the Galilean satellites are around Jupiter, they're pretty much in the same sort of orbits. They're way, way, way inside the orbit, well, not way, way, but we're way inside the orbit of Mercury in terms of distance. So Mercury's there for scale. Okay, so the outer one of the TRAPPIST planets is outside the orbit of Mercury. Okay. So this system is very interesting for that sake. What's interesting also about this, though, is that at least 2 of those, and possibly 4, are within the Goldilocks zone. Because this is a much smaller star than the Sun, so its Goldilocks zone is much closer in, because it's much less bright, much cooler. And so the Goldilocks zone actually overlaps where these planets are in this system. So there are Earth-like planets, 2 of them at least, with potential for liquid water. Although before you get too excited, it turns out they're probably all tidally locked. So this is a very strange system in the sense that they all are a bit like the Moon. They're all tidally locked to the star, and so the same face faces the star all the time. So what that means in terms of liquid water is difficult to work out. They're probably not likely to host high-level life, because the star is also not very stable. It's a small star, so we've measured one Carrington scale event already in the time we've been looking at it. So the planets, the radiation levels are very high, but still it shows you the possibility of Earth-like planets with liquid water on the surface around other stars is certainly there. And this is an amazing system. It's amazing for another reason, and that is that all these planets are in a resonance. We talked a bit about resonances earlier. So they're all in resonant orbit. So the outer one goes round, the inner one goes around 12 times for every once of the outer one. And all the others are in different resonances, 3 to 2 resonances, 3 to 4 resonances. They're all in resonance with each other. So this whole system is a resonant chain. It's the longest resonant chain we currently know of. So it's a 7-planet resonant chain. So it's an incredible system. And one of the things you can interestingly do with a resonant chain like that.
Does that mean they're all moving out?
No. That only happens when you've got debris to cause it to shift. This is a clean system now, so they're not shifting. They're staying in those orbital systems. So one of the things you can interestingly do is to convert that into music, because they're periodic and they're in a resonance. So if you play a note every time it passes, you make this music. Yeah. It's amazing, isn't it? So they're just playing a different note every time each of the different 7 planets crosses. And because you hear the resonance, right? You're hearing the fact that it sounds like music because they're in resonance. They're not random.
That's amazing.
Yeah, amazing. So just to wind up, what's the future of this? Well, as I said early on, there are lots of ways of detecting extrasolar planets. Like the Kepler system, the transits is one way of doing it, but there are actually lots of other ways of doing it. And we're entering into a sort of golden era of detecting extrasolar planets. And the plan for the next sort of 20 years is we'll have hundreds of thousands of extrasolar planets by the end of that period. We've already gone past 5,000. Okay, so we already have good statistics on useful things. For instance, we know that about 4% of the planets we've detected are sort of Earth-like, so they're solar mass planets. Quite a lot of them are supermassive, so big Jupiters. Quite a lot of them are gas giants, Neptunes, that sort of thing. And that's just because that's how the detection mechanisms we've used to date have been sensitive to those. But even within that set, we've got hundreds and hundreds of Earth-like planets. And so the lead from NASA said recently that it was sort of inevitable that within this period we'll detect sort of an Earth analogue with liquid water in a reasonable orbit. I mean, we're going to see many, many, many. So look here, what you want to be looking is how many of them are going to be Earth mass, so 1 on the left and 1 year on the right here. How many of them are there? And you can see that part of the diagram really fills in. So in the next sort of 20 years, we're going to have Earth analogues, lots of them. Basically, planets seem common. There's nothing surprising about the physics of how the solar system formed. I mean, it's surprising, but there's nothing I think we understand the basics of that. We're making big progress in this field. And so within a relatively short time frame, we're certainly going to have Earth analogues. So yeah, there we go. Thank you very much. I was asked to leave some time for questions.
Thanks
so.
very much, Fraser. Any questions?
right.